All right. Hello, everyone. While they pull up my slides, thank you for seeing the title of my talk. Now I don't have to. It's quite a mouthful. All right. So I will tell you about grains and rover wheels once I can see it. All right. So tribocharging refers to the charge exchange between two materials when they come into contact. And so specifically on the lunar surface, we know that at the polar regions, the surface can become triboelectrically charged. So when we have objects like rovers that are moving around in these areas, charge can be transferred from the lunar surface to these objects. And that can pose an electrostatic discharge risk to astronauts, and it can also interfere with the electronics on the rovers, for example. So my project focuses on modeling this tribocharging between the lunar surface and rover wheels. So we get two different types of tribocharging. The first one is same material tribocharging, so between two insulators or two conductors. And then the second type, which is where my work focuses, is different material tribocharging, which is an insulator and a conductor, or in this case, the regolith and a rover wheel. So the model that we use to look at this tribocharging is called a patched surface model. And so with this model, we create a synthetic surface using a stochastic algorithm. And so I'll just kind of like quickly go through how we create these surfaces. So we start with a smaller matrix, which is A there, which just has random numbers from a Gaussian distribution in it. And then going from A to B, we kind of like pull those random numbers apart and fill them with blank spaces. And then from B to C, we interpolate in between those initially random numbers. And then to go from C to D, we have a thresholding equation, and that basically tells us if a site is going to be a donor, so that's the pink spots, or an acceptor, which is the blue spots. And so once we have the surface, charge can be exchanged between the donor and the acceptor spots. So to model this charge exchange, we use a discrete element modeling software that we call LIGHTS. And so what we do in LIGHTS is we model the particles. We can model like thousands of particles, and each of those particles represents a grain. And when we model these grains, we can envision the patches on the surface of the grains. So that's these spheres here. So the gray spots will be donors, and the light gray spots will be acceptors. And so we can then, as these grains are like contacting, we can transfer the charge between the two of them. So this patch surface tribocharging model has been implemented in LIGHTS by a postdoc from our lab. And so she validated this model with insulator-insulator contacts, which is awesome. So we know that it's been validated for one type of contact electrification. And so then what I'm trying to do is to validate it for different material tribocharging, right? So insulator-conductor contacts. So how I will do this is I will have three steps. The first one is to validate grain STL interactions in LIGHTS. So I want to do this because if I have, so the top picture up there shows a grain bed with like a wheel on top of it. If I want to model the interactions between grains and wheels, it's much easier to have a CAD file or an STL file for a wheel because it's easier to make more intricate shapes, and it also reduces computational complexity since I don't have to make a wheel out of grains. So that's the first thing, is we need to validate that the interactions between grains and STL files are correct. The second thing we need to do is we need to expand our LIGHTS implementation of the tribocharging model to include these STL files, because right now the tribocharging is only implemented for grain-grain interactions. And then finally, once we have done steps 1 and 2, we can replicate experimental results from a paper by Yao et al. To look at, to validate our model for insulator-conductor tribocharging. So in validating the grain STL interaction, so this figure here, we have the blue grains, which are initial conditions or an initial state, and then the pink grains, which are a final state, and the red line, which is the ground, that is just like an STL plate at the bottom. So this is kind of how we validated grain STL interactions. So the first one, for the normal force, what we wanted is you drop the particles and they just drop on top of each other and there's no movement. For both the sliding and the rolling, what we wanted to see is that the particle either slides or rolls across the surface and then stops after a certain amount of time. For the oblique impact down here, based on the grain properties and the surface properties, there is an impact angle where the impact would go from being a sliding impact to just like a bouncing impact. And so we can validate like kind of what that angle is. And then for the last one, for the spinning interaction, what you expect is if you just spin a particle on a surface, eventually it stops. So all of these interactions behaved very well, and we got perfect validation, which was awesome, except for the spinning interaction. So what happened was I would spin a particle and then it would just never stop spinning, which was crazy. So after digging into the light source code and figuring out what was going on, I realized that the addition of the normal force component for damping when you're rotating a particle, that addition is not accounted for between STL files and grains. However, it is accounted for between grain-grain interactions. So it's a very odd thing that was happening, but now I needed to determine like if this was going to be a problem and then figure out how I was going to address it if it was a problem. So what I did was I had a normal rotation simulation. And so the video here, it shows a giant light grain falling into a bed of smaller light grains, and it'll start spinning in a second. So it shows the angular velocity of the big grain. And so the graph here is just the angular velocity of the large grain in the z direction over time. And so I did the simulation twice, both with the normal component of the rotation force taken into account between the grains and also with it not taken into account. And so that's what the two lines on the graph here represent. And so what we see is that the behavior between the two lines is pretty similar, which is awesome. So we can conclude that if we are to replace that giant grain with a wheel, the fact that the normal component of the rotation isn't taken into account for those interactions shouldn't be a problem. So what we're working on next, like I said, is we're implementing the TRIBOCHARGING for STL files and lights. And after we've done that, we'll be able to compare that with experimental results. So the paper by Yao gives charge statistics for contact electrification with different wheel materials. And so after we've done that validation, we can go on to do some experimental work. So we want to predict the charge exchange between insulators and conductors, specifically in a vacuum environment. So we'll build like a little small experimental setup, which is either a wheel moving through, like rolling over some grains, or a drill drilling into some grains. And then we can look at kind of what the TRIBOCHARGING in those situations will be, and then compare that with our models.
2 minutes.
Well, that was perfect. Thank you all for listening. Please email me if you have questions.